So in this question, we're going to look at the ability for eyes to resolve two distant points of light. Those points of light will be the headlights of an oncoming car. And we're told that the headlights are 1.2 meters apart. We're told a couple of things about the eye. We're told that the pupils of eyes are going to be typically about 7 millimeters in diameter when they are kind of at their maximum. So in the dark, when you're trying to get as much light in as you can. Next, what we're told is that we're going to assume that eyes are diffraction limited. We're not going to worry about any other structural limitations. We're going straight to the physics of how our optical systems limited by diffraction, and that also tells us what equation to use. So what we want to know is at what distance these two light sources are marginally resolved. So that means that we can tell that there are in fact two sources of light, not just one. At a certain distance away, you'll just see one light. But as it gets closer and closer, eventually you can tell, oh, there's actually two. Now, this diffraction limitation of optical systems is dependent on a couple of characteristics. One, the D value. So the diameter here of the aperture is important, and we've been given that for the eye, for the pupil size. And the other part of this is the wavelength of the light. So the lambda value. And we've been told, well, let's use 600 nanometers for our lambda, which is a little bit on the longer wavelength side of the visible part of the spectrum. Now, the other subtlety here is that we're talking about imaging going on inside a medium, inside the eye. And so that means that we need to think about the fact that that's effectively going to be, well, it's going to be similar to water, actually. So we're given an N value here of 1.33, which is basically saying it's like water. Okay. So what do we want to use to calculate this? So I've drawn this out. We've got these two sources of light here and here. And they're at some small distance apart. We have some observer here. Obviously, this is not to scale. Well, what's going on here is we have a case where our minimum angle is going to be equal to our alpha, which is the angle created by this distance away from our lens caused by the separation between the two light sources. And so this is our criterion for marginally resolved. These two are going to be equal, and this is going to be equal to 1.22 lambda over d. This is our criterion for being able to resolve two things. And so as a reminder of what these angles physically mean, we can go to this diagram. And so in this case, we have two objects, and I've noted here that in this case, they're 1.2 meters apart. And in this case, this lens has a diameter of 7 millimeters. And so we see that this alpha angle is caused by the result of this distance away from the object. And so that's going to be useful because that's what we are ultimately looking for. And then this distance between the two of them. And then this theta term is important because that's telling us the case where these two are going to be seen independently, right? These two images produced by this system are not going to overlap entirely. So at a certain distance, when it's much farther away, these two patterns are going to be right on top of each other, such that you only really perceive one light. But at a certain point, either your system gets better or they get closer, and these are going to separate. And that produces this ability to distinguish between them, resolve them. Okay, so back to our question at hand. So we put down all our information, and we're trying to see, at what distance we're able to resolve this. Well, let's start thinking about this equation here. We could be tempted right away to say, well, I have a value for my d, that's 7 millimeters, and I have a value for my theta. But here's where we've got to be careful. This is not going to be the lambda term that we want to use, because the imaging going on is within the eye. So let's take a look at the eye here. So I'm just going to draw this out and remind ourselves that what's going on is within something that has an n value. So inside the eye, we're told the n value is 1.33. And obviously outside, we have the air, and that's got an approximate n value of 1. It's just a little bit more, but it's basically 1. Okay. And we've got this imaging, it's going on a detector in the back of your eye. So we have to consider, well, what is not just the wavelength out here, which is what we were given. That was 600 nanometers. But we also have to consider, well, what then is the wavelength inside the eye? Well, let's work that out. And let's remind ourselves of a couple of things. One, what is the n value? Well, that's our index of refraction, and that's this ratio between c, speed of light in a vacuum, and the v in our substance. And so our case, we could say, well, our eye. This will be our eye. Okay, well, c, the speed of light in the air is very similar, especially when we're comparing it to water or glass or anything. So we could think about c as basically being the ratio here with air. And so we also know from waves that the velocity of a wave is equal to f lambda. So kind of recall. Okay, so what is c then? Well, it's basically equal to the frequency of the wave in air or in a vacuum times lambda in air, and this is over f in the eye times lambda in the eye. Okay, well, the thing is, when we have light waves going into a medium, the frequency does not change, but the wavelength does. So those frequencies cancel, and so what we have are the two lambdas. So basically, we can also define the index of refraction in terms of the ratio between the wavelengths. And so this gives us a way now of finding the wavelength of that light in the eye. And so that's going to be the wavelength of that light in air divided by our index of refraction in the eye. So we were at 600 nanometers. And our n value is 1.33. And so our new lambda wavelength value for this light in that context is going to be 450. So that will make a material difference. Okay. So now we've put this information in the proper context. You may have wondered, well, why did they give us an index of refraction of the eye? Well, this is why. All right, so now we can go back to our case here. So we've got our alpha. Well, we've got 1.22 times our lambda, and our lambda is going to be 450 nanometers. So we can say, well, that's 450 times 10 to the negative 9 meters. And that's all over D. And in our case, our D is going to be equal to, I can write down here, it's our 7 millimeters. Maybe I'll just note that. So our D value is 7 millimeters. That's our aperture. Okay, so that's 7 times 10 to the negative 3 meters. Okay, great. So let's get that angle. But that angle isn't really what we want, right? That is going to get us what we want. So what's our relationship here? Well, okay. Things around the eye are a little bit crowded, but let's do this. So let's just draw this out. So basically, I'm going to draw it just out to here, just so we get a bit of an exaggerated case. So I'm going to kind of consider, let's just say, here's our point where we have our eye. And we'll just, expand that there. So in this case, this is our alpha angle, right? And so then we've got this one length, which is 1.2 meters, and that's our headlight separation. And then we've got this length, this distance away, which is some value. I can just call this L. And that's what we're actually interested in. We're saying how far away can it be, and we still resolve it. So how do we write alpha in terms of these two distances? I'm just going to bring this down just a little bit, and we're going to do that right beside this little diagram. Maybe I'll just separate this, get this a little bit more organized. Okay, so what's our relationship here? Well, let's take a look at the triangle. We have our alpha is going to be an angle that is going to be equal to, well, we can put it in terms of its opposite and adjacent. So we can say, well, our tan theta here, but our theta is alpha, is equal to opposite, which is 1.2 meters, divided by adjacent, which is our L, and that's what we actually want. Okay, so let's put this in terms of just alpha. We can say, well, our alpha is equal to our inverse tan, 1.2 meters, divided by L. And so now we can actually just substitute this in for alpha in our equation and solve for what we want. Now here's where things get kind of interesting. The alpha here is really small, and so you can, strictly speaking, you can calculate this if we want, but we can also say, well, this is small angle approximation, and say, well, this is basically equal to 1.2 divided by L. And we don't need to worry about the trig aspect of this. Now you could do, and we can do this both ways just to show that's true. Okay, so our alpha value is then going to be equal to 1.2 meters over L. And now let's isolate L and get our length, our distance away. All right, so we're gonna bring the L over to the other side, and then so we're gonna have L is equal to 1.2 meters times our 7.0, our 7 millimeters, times 10 to the negative 3 meters, and divided by 1.22 and our 450 nanometers. And so, what do we get for our length? Okay, well, let's just check. 1.2. Okay, so we get a value here that is kind of 15, 300 meters. And we probably look at what we were given here and say that's, and we can call that 15 kilometers. So at a distance of 15 kilometers, headlights can be marginally resolved. It's actually pretty far. But remember too, we made an assumption that our eyes are a perfect lens, and that may not be completely true. And so that also means, right? So this also means that headlights will be fully resolved closer than that. So then we can just make a clear note to be really explicit that closer than 15 kilometers, headlights are fully resolved. Maybe I'll just keep this organized and move this up here. Oh. Don't want to bring the number, just want to bring the text. Okay, so that's an example of looking at whether or not something can be resolved at a certain distance away of a certain optical system. And if you want, you can, remember we did this little small angle approximation. If you want, you can work it through without doing that and see that it does not make a difference. Okay.